Alright, this is your video for 11.6. Only two more. This one and one more. Alright, we're adding three more theorems to this one. These actually have names, so they're kind of easier to remember, and they're named after what parts they're made up of. So it's really, this section's a lot easier than 11.4 and 11.5 were. This one's called the chord-chord product theorem, and when two chords intersect in a circle, they're actually inversely proportional to one another. So you'll learn about inverse variations more next year in Algebra 2, but this one naturally has an inverse variation to one another. How I remember the theorem is part times part equals part times part, and this will make a little more sense when we add on the other two theorems here in a minute. But basically you're just going to multiply the two parts of the chord back together. They were separated because the chords ran into each other, so we're just going to fix them by multiplying them back together. And it's easy to remember that it's multiply because it's called the product theorem. So 7 times 10 equals 14 times x. So then we can divide by 14. 70 divided by 14 is 5, so x is equal to 5. Then it says find the length of each chord. So chord FE, we already knew was 17, and chord GH is equal to 19. So it's important to remember the two chords aren't equal to each other like the tangents were, like the snow cone problem. They're not equal. They're inversely proportional. So they're not going to have the same length, but they are going to have a special relationship. Okay, let's check this out in a word problem style. I'm probably going to have to zoom out here. Alright, so the art department is contracted to construct a wooden moon for a play, and one of the artists creates a sketch of what it needs to look like by drawing a chord and its perpendicular bisector. Find the diameter of the circle used to draw the outer edge of the moon. Okay, so I'm just going to kind of come over here and zoom in on the picture since we don't need the other one. So the first thing we would want to do, if I had room, is we would want to extend the circle so that we could use all of our theorems that talk about circles and not just this moon here. Okay, so we're going to draw this in. We know this is a perpendicular bisector, so we know this half is 9 and this half is 9. And if we think about it, this is a chord and this is a chord. So we're going to be able to use our chord-chord product theorem. So basically, 9 times 9 is going to be equal to 8 times x. So x, this piece that we didn't know, is going to be equal to 10.125. Now it wants us to find the diameter. Now we know this is the diameter because we know that from that 11.2 theorem. If these are going to be the perpendicular bisector like it was in that theorem where we did this and we did the Pythagorean theorem, this has to be the radius, or in this case we're going to go all the way through, so it has to be the diameter. Any segment that is going to be the perpendicular bisector of a chord is going to be the radius or the diameter. So if this is 10.125 and this is 8, then the diameter is 18.125. What are we in? Inches. Okay, so this one doesn't really even look like a circle at first glance because it just has the moon. So we need to draw in the full circle and then recognize, hey, I have a chord, so I'm going to use chord-chord. Alright, the second theorem that you have is your secant-secant theorem. So it's made up when two secants intersect one another. Now, you know secants are lines, so these would actually keep going if they were true secants. These are what we call secant segments, and that's in your vocabulary chart too. It just means we're only going to talk about the part of the secant that we want to. We're just going to pick our favorite. So secant segment. So this is the secant-secant product theorem because this is a secant segment and this is a secant segment, so secant-secant. His relationship is a little different. I call it whole times outside equals whole times outside. Now this is the one people want to mess up because when you say whole, I mean the entire secant segment from start to stop. So for this side, for DE, the whole segment would be 16 times the outside segment would be 7. That one's pretty easy. Where you get messed up is you can on the variable side. GE, the whole segment is x plus 8. Now 9 times out of 10, people will go too fast and they'll put 8x instead of 8 plus x. And those are two wildly different things, and you don't want to be one of those people. So you might want to write that in the margin. 8 plus x times the outside is 8. Once we get our theorem on there, then and everything substituted in, then this just becomes an algebra problem. Sorry, my camera strap keeps coming down. Alright, so this is going to be 112, 8x plus 64. Don't forget we're distributing. So move the 64 and divide by 8, and x is going to be equal to 6. So x is equal to 6. So it says find x, which we did, and then it says find the lengths of the secant segment. So DE we already knew was 16, and now we can know that EG is 14. So again, these aren't congruent, but they do have a relationship with one another there. Okay, so the secant theorem. Pause here and try to do B by yourself. Alright, so here's B, still secant, whole times outside equals whole times outside. So you end up with Z is equal to 14. So when I go and plug that back in, LG was always 39. And now JG is going to be 27. Alright, the last theorem that we have from your theorem chart is the secant tangent product theorem. Excuse me. Alright, so this is a secant segment and this is a tangent segment. So their relationship, for secant, you still have that whole times outside. For tangent, you don't have two pieces to either add together or multiply together, whatever you need to do. So basically you use the same one twice, tangent squared. Whole times outside equals tangent squared is how I'll remember this one. Again, with the whole, make sure you're adding. So 20 times 5 equals x squared. So 100 equals x squared. So x is equal to 10. And this one just says to find the length of x, which is the segment. So x is equal to 10 is my final answer on that one. Okay, pause and you try B. Again, secant tangent, so whole times outside equals tangent squared. This time the variable's in the different place, so it just causes us a little bit of a different algebra take on this. 7 plus y, because remember we're doing whole, times 7 equals 10 squared. When I solve that out, y is equal to 51 over 7. Alright, see you tomorrow.